Well, we're going to work on a couple of things today. You ready? Are you ready? We're going to do a few things. We want to, first of all, we're going to solve system of equations by graphing. We're going to see what a system of equations is. And then we're going to solve it A, by graphing, which is really not a practical method. It lends some insight, but it's not a practical method for solving systems. We're going to solve them by using a method called the substitution method. And we're going to solve them using a process called the elimination method. There's another method for solving systems that we're going to work with later this week, but we're just going to work with these three today. And then finally, what I want to do is expose you to different types of systems of equations and help you to recognize how you distinguish what the different types of systems of equations are. Well, first of all, what is a system of equations? I'm going to give you this scenario. Think about this for just a minute. Suppose you have a 12-foot board. You want to cut it into two pieces. You want to cut it into pieces so that one piece is 2 feet longer than the other. I just gave you two pieces of information. There was a 12-foot board to begin with, and one piece is going to end up being 2 feet longer than the other piece. Those two pieces of information form a system of equations mathematically. Anytime you have two or more equations that simultaneously impose conditions on a variable, you have a system of equations. So here's the example I was just working with. Let's just take our board, our 12-foot long board. We're going to cut this thing. We're going to call one side of it x and the other side y. There's our two variables. Now, the fact that it's 12 feet long and the fact that one is going to be 2 feet longer than the other are two equations related to x and y. What's one equation you can write about x and y knowing that this board had to be 12 feet long? X plus y equals 12. That's an equation that's imposing restrictions on x and y. That is to say, x and y have to meet certain criteria. Not restrictions in the term that we've dealt with before, but just conditions that have to be met. The other fact is that one is longer than the other. So what equation can we conclude from that, assuming that y is the longer side here? There you go. Y minus 2 equals x. We have a system of equations. We have two variables, two unknowns, we could say, and two equations. And somewhere, somehow, there's a solution for x and y that will satisfy this. Now, that's not true with every system, but it is here. Just by trial and error, you maybe have been running the numbers through your head. You might notice what the lengths of these two pieces are going to be after we cut them. 5 and 7. Right. The solution to this turns out to be x equals 5 and y equals 7. Those are the two values that satisfy both equations. 5 plus 7 is 12. 7 minus 2 is 5. Well, that's the solution to the system. There's 4 common methods. We're going to look at one of them later in the week because it takes a little bit more time, though it's very slick. We can graph, we can substitute, and we can eliminate. What we're going to look at later in the week is Cramer's rule. We're going to start out by looking at a system and solving it by graphing. If we have a system of equations and we want to solve it graphically, we graph each equation. And that's going to lead us to two curves on the graph. And the places where they meet, those coordinates give you your solutions. So we want to graph our equations, look for the places where they meet, and those are going to be our solutions. Now here's a sample of a system. 2x plus y equals 5, 2y minus 4x equals 14. We want to graph those two equations. Now before we do it, before we can graph those, what do we have to do? You have to solve them for y. The top one, you'll probably agree without too much trouble, is going to become y equals negative 2x plus 5. Okay? The other one, if you solve it for y, I'm just going to save a little time and tell you what that turns out to be. That's going to become y equals 2x plus 7. That's right. There they are. There's our two equations. Now we're going to graph those. We're just going to use a typical piece of graph paper here to graph both of these lines and look for their point of intersection. The top equation, y equals negative 2x plus 5, we're going to graph that in red. The color might not show up very well on your screen, but note that this top equation is the one that we'll graph first. Our equation is y equals negative 2x plus 5. That means we've got a y-intercept of positive 5 and a slope of negative 2. So to graph that point, we'll go ahead to that y-intercept of positive 5, and we know that the line has to cross through that point. Then, since the slope is negative 2, we're going to go down 2 units and over 1 unit, and that'll give us another point on that line. And if we continue to do that, we'll have a series of points that will lie right on our line for our first equation, y equals negative 2x plus 5. Now, we're going to go ahead and do the second line, which is blue. We want to graph y equals 2x plus 7. Our y-intercept is positive 7, and we know that we're going to have a slope of 2, which means we'll have an increase of 2 units in the y direction, up 2 for every unit to the right in the x direction. So up 2 over 1, up 2 over 1, and again we've got a series of points here, and we can graph that line. Now, we've got our point of intersection. Let's zoom in on that for a minute. And we can see that these two lines cross very close to that location, which is given from our graph. We can see that that is an x-coordinate of negative 1/2 and a y-coordinate of 6. And so we found the solution to this system of equations. You can see that one of the problems with solving systems by graphing is the fact that our answer can only be as accurate as the lines that we graphed. That's why it's convenient to use graphing if we have some sort of computer software where our graphing is nearly perfect. We've solved this system. The solution to this system of equations is x equals negative 1/2, y equals 6. We could take the time to verify that these two values are the solution to the system. We can check that real quickly in the top equation. Negative 2 times negative 1/2 is positive 1. Add 5 and we do get a y value of 6. That'll also hold for the second equation. 2 times negative 1/2 is negative 1 plus 7 gives us a y value of 6. So that is in fact the solution to the system. And we're done. Of the two much more practical methods that we're going to do today, the first one we're going to take a look at is the substitution method. When you're substituting, you want to begin by picking one equation and solving it for a variable. We're going to plug that into the other equation, and that'll reduce the number of variables in our resulting equation. Step 1, you pick an equation and solve for one variable. Make life easier on yourself here. Choose the one, if there is one, that's the least work. So we can either take the top equation, solve it for x or y, or we can solve the bottom equation for x or y. We've got 4 choices. X or y in the top, x or y in the bottom. Now, in this case, they're all going to be the same amount of work. So let's choose the top equation, solve for x. If we do that, just to save a little space, what would I do to solve this top equation for x? Add 3y to both sides, right? Divide by 2. To save space, we're going to do that in one step and save a little time. X equals 13 plus 3y divided by 2. Everybody agree with where that, how we'd get that result? You're going to solve this one for x. You're going to add 3y to both sides. That'll get rid of that, and then we would divide by 2. 13 plus 3y over 2. So we've got x solved. Solved it for x. That's step 1. Step 2, you substitute it into the other equation. Don't plug it back into itself, or you're going to get nothing. You'll find the whole thing will cancel. You'll end up with nothing at all. So we're going to substitute. And we get 5y minus 4 times, okay, now here's where we substitute. We no longer have 4x, we have 4 times 13 plus 3y over 2. Equals 10. We've got an equation now with only one variable. We could solve that. So let's solve that. The 4 and the 2 are going to cancel here. And we're left with 5y minus 2 times 13, that's minus 26, minus 6y equals 10. Let's stop there for a minute. Everybody agree with that? I'm kind of condensing steps a little bit. Okay? 5y minus 26 minus 6y equals 10. Solving that, we can combine the y's. We can add 26 to both sides and combine the y's. We end up with 5y minus 6y, that's negative y, equals 36. And so we've got half of our system solved. We now know what y is. What's y equal to? Y equals negative 36. Okay, so we're half done. And now we need to find x. You have 2 choices here. Where do you want to go back to find x? Yeah, you could go back and plug it into one of your original equations, but then you've still got some algebra to do. Here you can just plug it into this equation because we found out what x was. So x equals 13 plus 3 times negative 36 over 2. And if you work that out, that's going to turn out to be negative what? 95 over 2, yep, negative 47 and a half. And we got our system of equations solved. Y has to be negative 36, x has to be negative 47 and a half. Before we go on, I'm going to give you one more problem to do of this type. I'm just going to give you a minute to practice it. I'll work through it up here, make sure that everybody's got the substitution method down, and then we'll go on to our third and final method. This one has decimals in it, but the technique is no different. Now, this time there's a little bit better choice. You can choose to solve this for whatever variable you want. But there's one that's going to mean a little bit less work for you here. Out of those, would you rather solve the top equation for A or B or the bottom equation for A or B? The bottom one for B, good. Because it's already almost done. So let's solve this one for B. Solve the bottom one for B. Okay, we clearly get 4a minus 14.8 over 6 equals b. Now we're just going to leave it like that. You could divide this out, 4 over 6, but the problem is if you divide this out and put 4 over 6, you're going to get 0.6666666. You've got to round that somewhere. Wham, you've introduced error into your system of equations. We're going to leave it just like that. Okay, now let's substitute that in to our top equation. And our equation becomes 1.5a plus 4.2 times, not b anymore, but 4a minus 14.8 over 6 equals 13.29. Okay, now we've got an equation with one variable to solve. That's just a linear equation. We've done that before. I'm going to have to leave the original problem up there to save some space. So we have, if we rewrite that now, you can cancel at this point. That turns out to be 0.7. So we have 0.7 times 4a minus 14.8 equals 13.29. Continuing to solve here, we have 1.5a Okay, everything look good okay so far? Okay, well we can wrap that up then. We can add 10.36 to both sides and combine our a's. (1.5a) and 2.8a is 4.3a equals 23.65. Right? 23.65. Solving for a, divide both sides by 4.3. A equals 5.5. A equals 5.5. Okay, so we're half done. Now we can go back to what we have right here. We know that b is 4a minus 14.8 over 6. We know what a is. We can find b. So 4 times a, which we now know to be 5.5, Four times 5.5 minus 14.8 divided by 6 turns out to be 1.2. That's right. So a equals 5.5, b equals 1.2. Again, even though it's not x and y, these answers are often expressed in ordered pairs, typically in alphabetical order. So we could say that the solution here is 5.5, 1.2. And we solved it, again, using the substitution method. Well, the third method is the best, okay? The third method, most of the time, except for Kramer's method, which we're going to see later in the week, which is very slick, we're going to use the elimination method, which is my favorite and will likely be yours. You can change the appearance of equations by multiplying an entire equation, or both, if the case need be, by some constant value. And the point of doing this is that equations with similar terms can then be eliminated, and you can get rid of one variable right off the bat. In the bottom equation, we have negative 4x. The top equation, we have 2x. What can we multiply the top equation by so that all the x's will cancel with the bottom equation? 2. Positive 2, actually, because then I'll have positive 4x and negative 4x, and when I add them up, they'll be gone. So I'm going to take this top equation and multiply the entire thing by 2, because I'm choosing to eliminate x. And so I get the equation becomes 4x plus 6y equals 10. What are we going to do with the bottom equation? In this case, nothing. Sometimes we'll have to modify both. In this case, we don't need to do anything. This equation, we're just going to leave the way it is, and that becomes negative 4x plus 2y equals 30. The reason that we do that is because you can add equations together just like you can add expressions. But we have to make sure that the column is aligned. This one was set up so that the x columns, the y columns, and the constant columns all align. Now, 4x minus 4x is 0. See why it's called the elimination method? You eliminate one variable. 6y plus 2y is 8y. And 10 plus 30 is 40. Now, the key is that you can add or subtract equations to make your variables cancel out. We will always add them to avoid any sign errors. We always set it up so that one of the coefficients is positive, the other is negative, and when we combine them, they're gone. Well, if 8y equals 40, we've got y solved. Divide by 8. And apparently, y equals 5. We're half done. Now, since we aren't using substitution, we have to go all the way back to one of the original equations to solve for x. Doesn't matter which one we use. Let's use this bottom one. We know that negative 4x plus 2 times, not y anymore, but 5 equals 30. So 2 times 5 is 10. We can subtract 10 from both sides here. And we have negative 4x equals, those are gone, 20. And x equals negative 5. Just going to skip that division. We're running out of space there. Divide both sides by negative 4, and x equals negative 5. And so we have our solution. Negative 5, 5. Again, we could check these by plugging them in, make sure that both equations are true, but to save time, we won't do that. Aaron?
What if you were to take the y equals 5 and plug it into 4x?
No, the first thing you need to do anytime you're working with elimination is you need to rearrange the equations so that the x coefficients, the y coefficients, and the constant coefficients all line up. So I'm going to rearrange those as I write them on the board so that that happens. Okay, this time, to mix it up a little bit, let's eliminate y. What's your common coefficient on y going to be here? 6. So let's multiply the top equation by? Multiply the top equation by 3. It becomes 15x minus 6y equals 9. Okay, bottom equation? Times 2. It becomes 6x plus 6y. No, it doesn't. Not 6. How about 4x? Is that better? 4x plus 6y equals negative 1.4. Here again, the signs on the coefficient of y, negative 6, positive 6, when we add those, they're going to cancel. So we can add these up. We get 19x. Those are gone. Equals 9 minus 1.4, 7.6. Okay? Divide both sides by 19. And x turns out to be 0.4. x is 0.4. Okay? Now we have to choose one equation somewhere, and as long as you haven't made any mistakes, which is kind of the idea, we can find we can find y using any of those other equations. So let's go back and grab this one. So now we know that 5 times 0.4 minus 2y equals 3. 5 times 0.4 is 2. Y is negative 1/2 or negative 0.5, and so we got it solved. Okay? Elimination method. Lot less algebra. Lot less. Okay. Now what we want to do is look at what other things can happen. All these have worked out nicely. We got our solution regardless of what method, but that doesn't have to be the case. So there's basically 3 things that can happen when you're solving a system. Here's the first one. These were independent systems. All the ones that we've done so far have been independent. Key word being independent, meaning that these 2 equations were independent. That is to say they were different. They had different information in them. If you have an independent system, that means you have a solution. And graphically, it means that each equation is different, but that they cross somewhere. Long story short, an independent system has a finite number of solutions. It could have 1 or 2 or 4. That's that. Now, the first graph that we did, I'm going to put a picture of this back up here. The first graph that we did was an independent system. Independent, remember independent in this way. Independent means that these 2 lines have independent information. This is one set of criteria. That's a completely different set of criteria, but there is a solution. So graphically, that's what we get when we have an independent system. Okay. Well, what are the other 2 things that could happen? Finding this system, solving it, and getting a solution is only one of 3 things that could happen. What are the other things that could happen? Okay, there's another thing that could happen. They could be parallel, or you could have a dependent system, which means, well, we'll get to that in just a minute. Here's an example of a dependent system. I want to show you what happens when you try and solve this. The first thing to notice when we look at this system is that our columns don't align well. In the first column, we have an x term above and a y term below. The second column, we've got a y term above and a constant term below, and so on. We need to rearrange those equations so that the columns align. Now, we can leave the top equation the way it is. We can rearrange either one, really, but we'll just leave the top equation written as 5x minus 2y equals 3. And we'll rearrange the bottom equation so that the columns align. I won't show the algebra, but we can simply subtract 4y from both sides, and that'll leave the equation 10x minus 4y equals 6. Those are the same 2 equations rearranged so that our x terms all fall in one column, our y terms fall in another column, and our constant terms are in the third column. Now, let's use elimination to eliminate one of these variables. It's very convenient to eliminate the x terms or the y terms. We'll eliminate the x terms. Let's take this top equation and multiply it by a factor of negative 2. Now, when we do that, we'll get a new equation. Here we'll have negative 10x plus 4y equals negative 6. The bottom equation we won't modify. We have 10x minus 4y equals 6. Now you'll note at this point that these two equations are almost exactly the same. The only difference is that each of the terms has the opposite sign. That means that these two original equations are really the same information, but that the bottom equation was multiplied by a different factor. For example, if you take this top equation and multiply every term by 2, you get the bottom equation. That means that there really aren't two separate equations there. There's really only one, and the second one is a modification of the first. Therefore, we have a dependent system. But let's continue. If we eliminate those x terms, we have no x terms left. When we add 4y to negative 4y, we're left with nothing on the left side. Everything cancels. That's also the case on the right side. Negative 6 plus 6 is 0. This result of 0 equals 0 means that these two equations entirely eliminated each other. This is an example of a dependent system. Anytime we end up with 0 equals 0 and we solve by elimination, we've discovered a dependent system, meaning that there was really only one useful equation there and the other one was some modification of the first. Now, what do you suppose you're going to get if you were to graph those two? They're the same curve, or the same line in this case. There they are. You can't see it too well on your screen, but they are both there. They're just lying right on top of each other. How many solutions are to that? How many points will satisfy both equations? Infinite. Millions of them. Any point that satisfies one equation will satisfy the other one. And so this has an infinite number of solutions. So they can be separate lines that cross. That's independent. They can be the same line, which means they're dependent. The last thing that can happen is a case like this. Suppose we have 5x minus 2y equals 3. Also, try this again, 20x minus 8y, thank you, equals negative 15. Let's eliminate the x's. Let's multiply the top equation by 4. We get 20x minus 8y equals 12. Bottom equation we won't mess with. 20x minus 8y equals negative 15. Now, how can that be true? How can you say 20x minus 8y equals 12? Oh, no. 20x minus 8y equals negative 15. Well, try to continue out. Subtract these. 20x minus 20x is 0. Negative 8y minus negative 8x, 0. 12 minus a negative 15. Is that ever true? 0 is not equal to 27. This is an inconsistent system. That is to say, are there any x and y values that are going to satisfy both of these equations? It's not going to happen. Okay? The previous example, every x and y that satisfied one would satisfy the other. There was million solutions. Here, there are none. Now, what's that going to look like when you graph them? If there's no solutions, what has to be true about these two graphs? They can't touch. Okay? If they're lines, that means they have to go on forever. They'd have the same slope but different intercepts. And so there's no solution. Those are the three types of systems you can have. Independent, which 90% of them are. Dependent, which means you have many solutions, infinite number of solutions actually. And inconsistent, which means you have no solutions. Those are the different cases that we can have. Let's take a look at this example. We want to solve this system. We want to solve it as efficiently as possible. It's still a system, a linear system. It's just that we have fractions in it. Find a common denominator and clear out the fractions. Okay, so for each one of those equations, we're going to decide what the LCD is and clear out the fractions. Then we're just going to have a regular old system. So we don't have to find a common denominator for both. We can just do them one at a time. For the top equation, what common denominator is going to clear them all out? 15. So we're going to multiply every equation by 15. Or excuse me, every term in the top equation by 15. Now, of course, we're going to get some canceling. 15 and 3 cancel and leave 5. Those cancel and leave 3. And here we don't have a fraction at all. So what does the new system become? Let's take this top equation and write it down here. Our first term becomes 35x. Our next equation becomes plus 6y. And our final constant term becomes negative 255. Okay, what about this second equation? Here we're going to multiply both of those by an LCD, and in this one the LCD becomes 45. So we multiply by 45. We get some canceling. 5 and 45 become 9. 5. And this equation we'll rewrite, and it'll become 18x plus 20y equals 14 times 45. 630? Thank you. Once we've cleared the fraction, it becomes the exact same kind of system you could have solved yesterday. So now let's take a look at that. Now I'm going to erase the original one just to gain some space, but the whole thing is simplified to this. Everybody clear with where those fractions went? Okay. Any thoughts? There's no right or, well, there are plenty of wrong answers, but you have several right answers to choose from here. What do you want to eliminate, x or y? Let's eliminate y. It's going to be a little bit easier. We'd have to multiply. They'd get pretty ugly for the x, but let's just multiply the equations by some value that will give us a common coefficient on y. 6 and 20. What's the first value we're going to hit here? 60. So let's multiply this top equation by what? Let's multiply the top one by, we could go either way. Let's do 10. Bring that one back up here. We end up with 350x plus 60y equals negative 2550. Okay. Now let's take the bottom one and multiply it by, we want to multiply it by negative 3. I was getting ahead of myself there. Multiply that by negative 3, negative 54x minus 60y negative 1,890. Okay. Well, now we can combine these two equations and eliminate the y's. We end up with 350x minus 54x, that's 296x, equals negative 2550 minus 1890. Negative 4440. Okay. Well, now we can solve for x. Divide both those by 296. What does that work out to? Negative 15? X is negative 15. And then we can go back and find y using any of the original equations, or we can grab one of these, assuming we haven't made any mistake. I'm going to go back and grab the equation we had a minute ago. Well, I'll just grab one of these since it's here. 350 times negative 15 plus 60y equals negative 2550. That's just a linear equation to save some time. I'm going to tell you that if you solve that, you will get y equals 45. And our solution is that, negative 15, 45. Okay, now I want you to go back and look at the original problem for a minute and notice one very important fact. Where were our variables? They were on the top. They were all organized in columns, the x column, the y column, and the constant column, but the variables were on the top. If the variables are on the top, we can just clear out the fractions and there's no trouble. If the variables are on the bottom, we have a little bit different issue. We can still take care of it simply, but we have to take a little bit different approach. Notice that for this one that the variables were on the top. We're going to do one last example, and in this case the variables are going to be on the bottom. We're going to take a little bit different approach to that. While I'm writing this and while you're jotting it down, think about this. Why can't we use the same technique that we just did? What's going to be the problem with just clearing fractions like we did? Here's the trick. We're just going to get rid of the fractions. We're going to do it like this. Don't you agree, first of all, that you can rewrite this equation in this way? I can factor that 6 out. And if I factor a 6 out of that one term, not everything, just this one term, what's going to be left here? 1 over x, right? This is the same as writing 6 times 1 over x plus, I'm going to do the same thing with the 4. 4 times 1 over y equals negative 2. Do the same thing for the bottom equation. This becomes 9 times 1 over x minus 7 times 1 over y equals 10. Now that's really just a system. If we just had 9x minus 7y and 6x plus 4y, it would look just like everything else we've done. So what we're going to do is we're going to make a little substitution. We're going to give these things names. We're going to let the reciprocal of x, 1 over x, we're going to give that a name. You get to choose whatever name you want. I like a. A is going to be equal to 1 over x. And we're going to give another name to 1 over y. Any suggestions? B, I like it. B equals 1 over y. Well, if that's the case, we can rewrite those systems, popping in those values, and then it just looks like a normal system of equations. So, the top equation will become 6, not 1 over x anymore, 6a plus 4b equals negative 2. And the bottom equation becomes 9a minus 7b equals 10. Okay, well that's not bad at all. We can solve that system. Let's use elimination. It's most of the time the most convenient way. What variable do you want to eliminate? Uh-oh. Either one would be fine. Okay, either one would be fine. Let's eliminate the b's just because they are opposite signed. The a's would be convenient because 18 is an easy coefficient hit. But since the signs are already opposite, let's eliminate the b's. Let's multiply the top equation by. Multiply the top one by 7. We end up with 42a minus 28b, plus 28b equals negative 14. And let's multiply the bottom equation here by 4. And we get 36a minus 28b equals 40. Now let's add those up. 42 and 36a is 78a. B's are gone, equals 26. 78a equals 26. So what can we conclude from that? A is equal to 26 over 78. A is 1/3. Okay, well, we now can figure out what the value of x is, but we'll do that in just a minute. Now we need to go back and we need to figure out what the value of b is. I'm going to erase this original part to save some room here. Now we know that a is 1/3. So let's grab one of these equations and solve for b. We can't use those because we don't really know what x and y are. Well, we kind of do, but these are the ones involving a and b, so let's grab one of these. Let's grab this one. 6 times 1/3 plus 4b equals -2. 6 times 1/3, 2 plus 4b equals -2. Subtract 2 and we have 4b equals -4. So b equals -1. Now we're not done. We still have to go back and figure out what x and y are, but that's a piece of cake. Because there's our a value. Here's our b value. A is the reciprocal of x, and b is the reciprocal of y. So we basically need to flip these back over to find a and b. Let's go find x first. A equals 1 over x, which is, what did we say? 1 over 3. 1 over 3. So what is x? X equals 3. And b equals 1 over y, which we know to be -1. And so what is y? Y equals -1. And we're done. We found our solution. X is 3, y is -1. The key is to make this little substitution. You factor out any numeric numerator, so it just becomes a 1. You say that a is the reciprocal of x, b is the reciprocal of y. So then when we're done, all we need to do is go back and take the reciprocals of a and b. The reciprocal of a was 3 over 1, or 3. The reciprocal of -1 was -1, and we're done.